Hey, welcome to the Explainer. Some of the most important things in engineering, like the flow of air or water, are totally invisible. So, how on earth do you measure something you can't even see? Well, the answer, as we're about to see, is actually pretty ingenious.
I mean, it sounds like a simple question, right? But think about it. If you're designing a skyscraper, or you're a pilot, or you're just curious about the weather, you need a real, precise answer. You can't just stick a ruler out the window. So, where do you even start? Okay, so our first clue actually comes from just watching how a fluid, and that can be air, water, whatever, moves around an object. See how it kind of splits and flows in these neat lines? We call those streamlines. And that pattern, that flow, it's holding a secret to finding our answer.
All right, so here's the challenge. How do we get a hard number for the velocity of a fluid, whether it's rushing through a pipe deep underground or just blowing across an open field? The trick isn't to try and catch the fluid, but to get clever about understanding its basic properties. And this is where we bring in a big gun from physics, Bernoulli's principle. Now, all it really says is that there's this tight connection, this relationship between how fast a fluid is moving and the pressure inside it. Basically, when speed goes up, pressure goes down. It's this incredible balancing act, and it is the absolute key that engineers use to crack this problem wide open.
And to tap into that secret, we've got to zoom in on this one specific, almost magical thing that happens every single time a fluid runs into an object. Okay, take a look at this diagram with me. You see all these streamlines flowing from left to right, right? Most of them just kind of bend and curve gracefully around the object, but pay close attention to that one right in the middle. It heads straight for the tip of the object at point 2, and then it just stops, dead in its tracks. And that exact spot, it has a name. It's called the stagnation point. It's the one and only place in this whole picture where the fluid comes to a complete, total standstill. And believe me, this isn't just a fun fact. It is everything. It's the entire basis for how we're going to measure the flow. So why does this happen? Well, you know that rule in physics, right? Energy can't be created or destroyed. It just changes form. So all that kinetic energy, the energy of motion that the fluid had, it has to go somewhere. And right here, at the stagnation point, it converts, one for one, into potential energy, which we can measure as a big spike in pressure. Okay, now this is Bernoulli's full-blown equation, and yeah, it looks a little scary. But don't worry, we are not going to solve this thing. We're just going to be clever. We know that at our special spot, the stagnation point, that's point 2, the velocity is 0. And because v2 is 0, that whole part of the equation just, poof, it disappears. And that makes things a whole lot simpler for us. And what we're left with is this really beautiful, simple idea. The total pressure you can measure right at that stagnation point is just two things added together. It's the fluid's normal, everyday pressure, we call that static pressure, plus all that extra pressure that got created when the flow was forced to stop, and we call that dynamic pressure. So that's the theory, but how do you turn that into a tool you can actually use? Well, an inventor named Henri Pitot took this exact principle and created a device that is just shockingly simple and effective. The original Pitot tube was basically just 2 pipes in the water. One tube faces straight into the flow right at point 2, so it's perfectly positioned to feel that maximum stagnation pressure. The other tube, over at point 1, has its opening on the side, so the flow just kind of glides past it. That way, it only measures the normal static pressure. Here's a good way to think about it. Static pressure, that's H, is like the normal air pressure you feel around you, all the time. But stagnation pressure, H, is like the extra force you feel when you stick your hand out the window of a moving car. It's that normal pressure plus the force of the wind hitting your hand. And here's where the magic really happens. By simply measuring the difference between those two pressure heights, the H minus the H, we can pop that number into a simple formula and get the fluid's velocity. That's it. The bigger that gap between H and H, the faster the wind is blowing. It's a direct translation from pressure to speed. Now, using 2 separate tubes works, but like with any great invention, the first version is a bit clumsy. So of course, engineers immediately started thinking, how can we make this better? How can we make it more elegant? And just look at the difference. On the left, you've got the original clunky 2-tube concept, and on the right, the modern pitot-static tube. It's such a beautiful evolution, combining both of those jobs into one sleek, compact instrument that you'll see on everything from Formula One cars to jumbo jets. And the design is just so smart. There's one tiny hole right at the tip to measure that head-on stagnation pressure. Then, there are a few other little holes on the side to measure the regular static pressure. Both of those pressures are fed into a single gauge that automatically shows you the difference, which makes the whole process way faster and more accurate.
Okay, so we have this amazing tool, but there's just one more little real-world wrinkle we need to iron out.
And this is a really important problem to solve. See, inside a pipe, the fluid moves fastest right in the center, and it gets slower and slower as you get closer to the walls because of friction. So if you only measure the speed at the center, you're getting the maximum speed, not the average speed. And if you need to know the total flow rate, the average is what really matters.
Well, instead of doing something crazy like taking hundreds of measurements all across the pipe, engineers came up with this brilliant shortcut, a chart. This chart tells you the exact relationship, the ratio, between the average speed and the maximum speed, all based on the specific flue conditions, which get boiled down to a single number called the Reynolds number. So the whole process turns into this dead simple 4-step recipe. Step 1, you stick the bateau tube right in the center of the pipe to find the maximum speed. Step 2, you calculate your Reynolds number for the flow. Step 3, you find that number on the bottom of the chart, go up and find the correct ratio. Let's say it's 0.82. Finally, step 4, you just multiply your max speed by 0.82 and bam, you have the true average speed for the whole pipe. It's simple, it's repeatable, and it's incredibly powerful. So let's just pull all this together. We started with what seemed like a simple problem. How do you measure something you can't see? And it took us on this really cool journey through some fundamental physics and some seriously clever engineering. And really, this is the big takeaway. The whole secret wasn't about finding a way to see the flow. It was about figuring out how to stop it, just for a moment, at a single point, and in doing so, converting its invisible energy into a pressure that we could easily measure. It really makes you wonder, doesn't it? The solution here was all about changing perspective, and it kind of leaves you with this final, bigger question. What other invisible, seemingly immeasurable things in our world are just waiting for us to find the right way to look at them?